In part one of this video lecture, we introduced we kind of reviewed some basic things about the conservation of momentum, regardless of the type of collision. And then we started talking specifically about elastic collisions. And the thing you should know right away or remember, elastic collisions, not only is momentum conserved, but kinetic energy is also conserved. And that is helpful to have two equations with the same variables, because then we can solve for two unknowns. And most of the problems that we do from the book, we really don't actually solve for two unknowns. Instead, we use the momentum equation to solve for velocity, and then we can use this kinetic energy conservation equation to check and see if the collision was elastic or not. And if kinetic energy before the collision is equal to the kinetic energy of the objects after the collision, then kinetic energy was conserved and we did have an elastic collision. But what I did here in the derivation section was I did a whole bunch of work on a different piece of paper, and I solved these two equations together, this system of equations, for the final velocities of objects A and B. And that's often interesting. This is an interesting problem because a lot of times we know the initial conditions, like there's two objects and they're moving towards each other, or one object's at rest and the other object is moving with a particular velocity, and we want to know what's going to happen after that collision. And so the first two questions down here really ask us to kind of think about this relationship. And again, these look kind of complex, I know, but notice that each final velocity, the final velocity of each of these objects, is really just a combination of the initial velocities. And how much of velocity A initially ends up in the final velocity of object A, and how much of the initial velocity of object B ends up in this final velocity depends on the relationship between these masses. So let's work a couple problems and see what it looks like. It says, the first one here, what are the final velocities after an object collides elastically with another object of equal mass at rest? And this is kind of a billiard ball problem. So let's think about that. So initially, we have an object here, object A, and it's moving with a velocity, and I'm just going to call that v sub A, and it's going to collide with object B, which is at rest. I'll just say at rest. And they're the same mass, okay? So let's see what happens with after the collision for object A. And if you look here at this relationship, then if they have equal masses, then MA minus MB, that's just zero. So this entire part of our equation here is zero. And then again, if MA and MB are equal, then on the bottom here we have like 2M, and on the top we have 2M. So this fraction becomes 1. And in fact, VAF is equal to VBI, which equals 0 meters per second. And I'm going to put an exclamation point there because that's a kind of an amazing little result. And you might know this if you play pool, that sometimes when you shoot the cue ball, it hits the other ball and it stops. And that's what happens in this collision. Let's go and see what happens to the final velocity of object B. Again, here, this expression right here is just 2m over 2m. That's just 1. And over here, mb minus ma, that's 0. So the final velocity of object B is equal to the initial velocity of object A. And so after the collision, and I'll just say finally, what we end up with is we got object A at rest, and we have object B moving with whatever object A's velocity was initially. And so really what happened was the momentum of object A was entirely transferred to object B. That's pretty interesting. Now, let's use this same relationship to understand what happens in this second problem. What are the final velocities after a small object at rest is struck elastically by a very massive object? Okay, so now we're going to have a really massive object A, let's say. And we'll have a tiny little object B right here. And this is at rest, and object A is moving with some velocity, and I'm just going to call that V sub A. Keep it simple. And let's look at we want to understand the final velocity of object A first. So notice, if the mass of object A is is a lot bigger than B, then we can, in this calculation, we can ignore the m sub b's, because if you have a big mass and you subtract a little tiny mass, you pretty much have the same mass you started with. And again, if you have a big mass and you add just a little tiny mass, you just have the same mass you started with. So this part of our relationship is just 1 again. It's ma divided by ma. And over here, right, if we ignore, if we know that mb is really, really small, and we divide by a really, really big number, ma, this becomes 0. So what we end up with from this result is that the final velocity of A is just equal to the initial velocity of A. And so I can just say the final velocity of A is going to equal this velocity right here. And let's do the same thing to try to understand what happens to the velocity of B. Now, again, just the mass of A is actually really big, and the mass of B is really small. So this becomes like 2 masses A on top and 1 mass A on the bottom. And so, adding this down here doesn't really change the denominator very much. So this just simplifies to 2. And once again, over here, we got the mass of B minus the mass of A. That's a negative mass of A, really, because this is like a really, really small number, and we're subtracting a really, really big number. And then again, on the bottom, it's just like it's just the mass of A again, because the mass of B is so small. So this becomes a negative ma over ma, which is just -1. But it doesn't even matter, because the initial velocity of object B in our situation is 0. So we end up here with like 2 velocity A initials plus a negative velocity B initial, which is really just 0. So the final velocity of object B is just 2VA. So that's another really interesting result. So what happens finally after this collision is that object A keeps moving in this direction. It's as if nothing, it just rolls right through object B and is not affected, because object B is so small. But object B definitely feels a lot, because it goes in this direction with twice the speed of object A. So it actually, object A comes barreling in here, it hits object B, and then object B goes shooting off with twice the speed of object A. That's another really fascinating result. And I'll just work this third one here, I think, because it's also related to this relationship that we're studying up here. What are the final velocities after a very massive object at rest is struck elastically by a very small object? So let me draw that situation initially. I've got a very massive object, and I'll call that object B this time. And object A is this little tiny object moving with a speed of A, and it's about to hit object B. So this very massive object is at rest, and it is struck by object A. So let's see what happens to the final velocity of A right here. If, remember, now in this example, B is much, much bigger than the mass of A. So we can ignore the mass of A in this calculation, and we get negative V sub AI, because if you just ignore these masses, you get negative MB divided by MB. That's just negative VA initial. And here, again, if the mass of B is really, really big and we ignore the mass of A, this just becomes 2 times the initial velocity of B, which is 0 anyway. So this whole thing just cancels out. So what are we left with? VAF equals negative VAI. VAF equals the negative of this initial velocity. And what happens to the velocity, the final velocity of object B? Again, object B is really massive. So this first fraction is really just 0, because we're taking a small number, twice the mass of A, and dividing by a really big number, which is about the mass of B. So this expression is 0. And then, of course, this is also 0 because the initial velocity of B is 0. So the final velocity of B is also 0 meters per second. And so again, what does it look like finally? We've got object B just sitting here. Let me just label this at rest. At rest. And then after the collision, the final velocity of A is the negative of the initial velocity of A. So it just bounces off object B and goes in the other direction. Just as you know, a tennis ball might bounce off the wall, or any object that collides elastically with a really big object like a wall that's stuck to the earth. It's just going to bounce off and go in the other direction. So that's interesting. I'm not going to work any more of these problems, but you should definitely try to answer question number 4 and think about that. And then on the back, there's 2 sample problems for you to work. And this got a little cut off by my printer, but there's some resources and some additional practice from the textbook, and I actually assigned a couple of problems for you to do that we're gonna check in about later. So go ahead and get those done. And if you have any questions, hit me up on the discussion on the Google Hangouts, or you can send me a message in any way.